This video is on revisiting partial fractions. I think one of the problem some students faced, it's not knowing which rule to use. And to know which rule to use, it is very important that we examine the denominators of the algebraic fractions that you're given. If you are able to categorize the denominators into linear factors, repeated linear factors, or irreducible quadratic factors, then most of the times you are able to know which rules to use. Right, so to start off, let us learn how to recognize linear factors. So linear factors are in the form ax to the power of n plus b, right, where n is the power and n must be 1, and a and b are constants. So if you look at this form ax to the power n plus b, there's only one variable, x, and the power must be 1, and a and b are constants. So some examples are negative 3x minus 2, right, because negative 3 will be a constant a, negative 2 is a constant b, and x means x to the power 1, right? So in this case here, the power is 1. That satisfies the rule stated above. Half x plus 5 is also a linear factor. Likewise, x minus 8. So what are some examples that are not linear? Right, if you look at the table shown, the first example is 2x cubed plus 3x to the power negative 2. This is not linear because there are two variables, right? X to the power 3 and x to the power negative 2. There should be only one variable. Right, if you look at the second example, there's only one variable, but this is also not linear because the power is 3. The power of x must be 1. The next step we need to be able to recognize is a repeated linear factor. So what are repeated linear factors? So previously we've learned to recognize linear factor. So repeated linear factors are actually two linear factors of the same kind stacked together. What do we mean? Let's have some examples. Supposing you have this linear factor negative 3x minus 2, and we have another of the same kind, right? And if you put them together, that will give you bracket negative 3x minus 2 to the power of 2. That is what it means by repeated. It's of the same kind, twice of it, and you put them together, and it becomes something to the power 2. Let's have another example. If you have a linear factor x minus 8 and another one of the same kind, right, you stack them together, and you will form bracket x minus 8 to the power of 2. So bracket x minus 8 to the power of 2 is a repeated linear factor. So supposing if you have a generic form, which is ax plus b, that is our linear factor we've learned earlier on in slide 1, or in the earlier slide, sorry, and another of the same kind, stack them together, and that forms our repeated linear factor. Alright, so we have learned how to recognize linear factor, how to recognize repeated linear factors. The next very important factors we need to recognize is called the irreducible quadratic factor. Okay, it's a quadratic factor. So to understand what are irreducible quadratic factors, let's recap on what is a quadratic factor. So a quadratic factor is in the form ax squared plus bx plus c. Alright, where the highest power is 2, and a, b, and c are constant. Right. And a not equal to 0. It's very important a not equal to 0, because if a is equal to 0, then you end up getting bx plus c, which is a linear factor. Okay, we're not keen, we have already learned what linear factors are, so we don't want a equals to 0. Right, so some examples of reducible quadratic factor. 2x squared plus 9x minus 5, you can actually reduce it into two linear factors, 2x minus 1 and x plus 5. For x squared minus 9, you can also factorize it into x plus 3, x minus 3. However, if it's an irreducible quadratic factor, then you cannot factorize it further. It's in the format x squared plus c squared. So one example is x squared plus 9. So it can be x squared plus 4, or x squared plus 3, or x squared plus 25. Okay? So hence, to know if it's irreducible, it is always x squared, then plus. The middle operation is a plus some number squared. Or another way to know if it's reducible or irreducible is to find the discriminant, okay, of the quadratic factor, right, which we will learn in the next slide. Way to recognize if it's irreducible or reducible is to find the discriminant. So if you look at the first example that we have on the table, 2x squared plus 9x minus 5, right? You can write down the values of a, b, and c, and you sub into your discriminant, b squared minus 4ac, and you get a positive value. So if you get a positive value, means this quadratic factor, if it's a positive value for your discriminant, means this quadratic curve has two real and distinct roots. It means that you can actually factorize it into linear factors, and from the linear factors you can actually find the root of the equation. So likewise for x squared minus 9, if you substitute into the discriminant b squared minus 4ac, you also get a positive value. So this is one way to recognize a reducible quadratic factor. If it's an irreducible quadratic factor, means when you substitute into your discriminant, you get a negative answer. A negative answer for discriminant means you have no real roots. It means that you can't actually factorize it into linear factor. You can't get any real roots. The curve will be above or below the x-axis. So that is irreducible quadratic factor. Okay, the two examples shown there is x squared plus 9 or 2x squared plus 2x plus 5. But in partial fractions, most of the time we actually deal with x squared plus c squared. Right, so let's practice what we have learned so far. All right, let's look at the table there. Right, the first example, 7x minus 3. Yes, this is a linear factor because it's in the format ax to the power of 1 plus b. So let's linear. The second example, you can actually factorize it further. X squared minus 1. You can factorize it into x plus 1 and x minus 1. So what you have here are two linear factors. Okay, x squared plus 5, we have learned early on, it's in the format of x squared plus c squared, and this is an irreducible quadratic factor. Okay, and for the next one, 2x plus 1 to the power of 2, this one is actually 2x plus 1 stacked together, 2x plus 1, 2 of the same kind stacked together. Okay, so this is called a repeated linear factor. Repeated linear factor. And the next example, what we have is the first one is in the format ax plus b, so that's linear. So we have one linear, and then this is in the form x squared plus c squared, that will be irreducible quadratic. So this example here, we have it comprised of a linear and a irreducible quadratic factor. How about the last one? The last one, you can actually factorize it further. It's a reducible quadratic factor. We can factorize it into 2x plus 3 and x plus 4. Right, so it comprised of two linear factors. Right, let's say if you're given this algebraic fractions 2x plus 1 over x minus 3 and x plus 4. Right, so how do I express it into partial fractions? Right, so what is the rule that I can apply here? Right, so let's examine your denominator. So your denominator is made up of two linear factors, right? X minus 1 is your first linear factor, and x plus 4 is your second linear factor. Right, so if that is the case, the rule that we use will be we let it equals to a is a constant over your first linear factor, plus, it's always plus, followed by b, another constant over the second linear factor. Okay, so we need to find the unknown a and b. A and b are the two constants that we need to determine. Right, so what do? We combine them into a single fraction. Right, and then we combine the we compare the numerator, because what we have done here is that we actually have already made the denominator of the left equals to the denominator on the right side. So hence the numerator on the left side will be equals to the numerator on the right hand side. So a bracket x plus 4 plus b bracket x minus 3 will give us 2x plus 1. Right, so we can use substitution method here. Right, so I can let x equals to 3 because there are two unknowns here. So I need to eliminate one of them, and I want to eliminate constant b first. So I'm going to let x equals to 3, because if I let x equals to 3, let's see what happens. I would have 3 minus 3, and 3 minus 3 is 0. So 0 times b, what does 0 times b means? It means you'll get 0. 0 times b means 0. Alright, so that will end up with 7a equals to 7 and a equals to 1. Right, so we have found constant a, so we need to find the constant b. Right, you can let x to be any numbers except x equals to 3 to find your constant b. So I'm going to let x equals to 0. So I will have a, you already found a to be 1. So you can actually substitute a to be 1, x to be 0, plus 4, plus b, 0 minus 3, equals to 2 bracket 0 plus 1. So that will gives you 4 minus 3b equals to 1. Negative 3b is equals to 1 minus 4 negative 3. b equals to 1. So therefore the partial fractions are 1 over x minus 3 plus 1 over x plus 4. Right, so if you have the denominator which is a linear, right, you can break it as a over x minus 3. If your linear factor, if your linear factor is x plus 4, then that would be, sometimes it could be a combination of linear and repeated. Right, so we'll do an example to show you. Supposing if you're given this algebraic fraction 2x plus 3 over x minus 1 and 2x plus 1 to the power of 2. and you ask to express it into partial fractions. So what is the rule that we can use here? All right, so let's examine the denominator. The first one, it's a linear factor. All right, so for linear factor, what is the rule to use? Yes, the rule to use is a constant a over the linear factor. So if it's a linear factor, it's a constant over the linear factor. Now, if you look at the second factor, this is a repeated linear factor. So what is the rule to use for a repeated linear factor? It will be plus b. You've already used up the constant, the letter a, then of course, naturally, the next letter you will use will be letter b. Okay, over 2x plus 1, then plus c over the repeated linear factor. Alright, so that is the rule to use. If you have a repeated linear factor, it will be a constant over the linear factor plus another constant over the repeated linear factor. Alright, so the next step we're going to do is to combine them into a single algebraic fraction. Find the common denominator. So we take a, you can cover up x minus 1. If you cover up x minus 1, then you're going to multiply a with your repeated linear factor. Okay, and then you cover up one of your 2x plus 1, cover up one of them. So you're going to multiply b with x minus 1 and 2x plus 1. Then you cover up your repeated linear factor, you multiply c with x minus 1. Okay, right. So we're going to compare the numerator. Right. So I'm going to eliminate my constant c. I think that's the and b. That's the easiest. Because if I let x minus 1 equals to 0, I will eliminate my constant c. I will also eliminate my constant b. So if I let x minus 1 equals to 0, then the values I need to substitute for x will be 1. Right? I need to substitute x to be 1 so that I will get 1 minus 1 equals to 0. Okay, so what do I have? I would have a bracket 2 times 1, that's 2, plus 1 to the power of 2. So b will be gone, c will be gone. So 2 times 1 plus 3. Oh, I think I better write here, let x equals to 1. Right, so I'm going to let x equals to 1. So I would have 3 to the power of 2. b will be gone, c will be gone. Equals to 2 bracket 1 plus 3. I would have 9a. 3 squared is 9. 3 times 3 is 9. So 2 plus 3 is 5. A is 5 over 9. Okay, so the next one I want to get rid of, I'm going to let 2x plus 1 equals to 0. Because if I let 2x plus 1 equals to 0, I will eliminate b. I will also eliminate a. Okay? So if I let 2x plus 1 equals to 0, that means the values of x that I'll be substituting will be negative half. Okay, so my a is gone, my b is gone, left only c. So c, negative half minus 1 will be negative 3 over 2. 2 times negative half and plus 3. So c will be 2 times negative half, 2 bracket negative half, 2 bracket negative half, then plus 3, then divide by negative 3 over 2. That will give you negative 4 over 3. Okay, so I'm left only to find the constant constant b. So I can just let x to be 0. Right, so I will end up getting already found the values of a, so I can just substitute it to be 5 over 9. 1 squared. I want to find b. And I found c to be negative 4 over 3. That gives me 2 of 0 plus 3. Alright, you can use a calculator to evaluate. You can use a calculator to evaluate this and this. (17/9). So you get negative b plus 17 over 9 equals to 3. Because 2 times 0 is 0, 0 plus 3 is 3. So b, negative b will be 3 minus 17 over 9 gives you 10 over 9. So hence your b will be negative 10 over 9. So we found the values for the constant a, b, and c. Now that's plugged into your partial fractions. So we will have 5 over 9 over x minus 1 plus negative 10 over 9 over 2x plus 1 and plus negative 4 over 3 over bracket 2x plus 1 to the power of 2. Now, we can't leave answer as in this form. It's not simplified, right? So I'm going to teach you one simple trick to how to simplify it. So 5 over 9, if you look at 5 over 9, the denominator is 9. So we're going to times 9 at the numerator, also times 9 at the denominator. Similarly, for negative 10 over 9, I'm going to multiply with 9 at the numerator, also at the denominator. So for negative 4 over 3, I can't times 9, because if you look at, I can if you want to, but it's easier to just multiply with the denominator here, which is 3. The denominator is a 3. So it's easier just to multiply with a 3. Okay, I'll explain to you why we want to do that. Because 5 over 9 times 9 gives you 5. Okay, I'm going to simplify it. We can't have a fractions over a fractions, right? So that's why we need to convert 5 over 9 into a non-fractions. So if you times 9, 5 over 9 times 9 will gives you 5. But you can't just multiply at the numerator. You can't just, you know what I mean? If I give you this fraction half, I can't just say times 2 and then to become 2 over 2. You're actually changing the question, isn't it? Okay, so if I have a half, if I want to multiply with a 2 at the numerator, then I must also times 2 at the denominator. So what you're getting is 2 over 4, which is actually originally equals to half. So you don't change the value of your initial equation. You don't change the value of your initial number of fractions you're given. So that will give you 5 over 9 bracket x minus 1. Plus times a negative will be negative. 10 over 9 times 9 is 10. 9 bracket 2x plus 1. Again, plus times minus is minus. So 4 over 3 times 3 will give you 4. And 3 over 2x plus 1 to the power of 2. So that will be your partial fractions. Supposing you're given a algebraic fraction, say 2x plus 1 over a linear followed by a irreducible quadratic factors. Let's say, okay, irreducible quadratic factors, if you recall, is in the format x squared plus c squared. So let's say we have x squared plus 2. And you ask to express that into partial fractions. So what is the rule that we can apply here? Okay, let's examine your denominator. This will be a linear factor. So for a linear factor, it will be a constant a over your linear factor. All right. Now, so your second factor is irreducible quadratic factor. Irreducible quadratic factor. So for irreducible quadratic factor, what's the rule that we can use? So the rule will be plus bx plus c. So at the numerator is a linear factor over your irreducible quadratic factor. Okay, so if you have used up the alphabets A, B, C, then the linear factor you need to use will be dx plus e. Alright, so you have a constant over a linear factor. And if you are getting an irreducible quadratic factor, then the numerator will be a linear factor. Alright, so what's the next step? The next step is we combine them into a single fraction. Okay, you can use the cover-up method, cover up x plus 1, so you multiply a with the factor x squared plus 2, and then you cover up x squared plus 2, you multiply bx plus c with x plus 1. Okay, here I need to remind you to bracket this guy, which is very important. You need to bracket here, you need to bracket your bx plus c, because if you do not bracket it, okay, if you write it this way, what you are saying is you are just multiplying x plus 2 with the constant c, okay, which is not your original intention. Your original intention is to multiply x plus 1 with bx plus c, right? So it is important that you bracket it. So you don't do it. You don't do, this is wrong. Okay, cross, this is wrong. All right, so now we can compare numerator. All right, so I'm going to let this guy equals to 0. Because if I let the guy equals to 0, then I can eliminate my constant b and c. So if I let x plus 1 equals to 0, then the values that I'm substituting for x will be negative 1. So I'm going to sub x equals to negative 1. So that will be gone. So this will give me 3a, negative 2 plus 1, negative 1. A will be negative 1/3. Alright, okay, I'm going to enumerate the constant b, so I can let x equals to 0. So I will end up 0 squared plus 2, which is 2. Okay, so b times 0 will be 0, so b will be gone, left only c. And then 2, 0 plus 1. So that will give me 2a plus c equals to 1. C is 1 minus 2a, and we can substitute the values of a we found earlier on. So c will be equals to 5/3. Alright, so I found the values for a, for c. Now I can just let x equals to 1 to find the values of b. So I've already found a to be negative 1/3, so I can put it in. 1 squared plus 2, that will be 3. I want to find b, so b times 1 is b. Found the values of c, which is 5/3, so I can put it in. And okay, 2 times 1 is 2 plus 1, 3. Alright, so we can simplify further. One third times 3 is 1, so 3 plus 1. Okay, so b plus 5/3 will be 3 plus 1, 4 divided by 2, 2. B will be 2 minus 5/3. Gives you 1/3. Right, so we found the values for all our constants a, b, and c that substitute into the partial fractions. So we would have negative 1/3 over x plus 1 plus 1/3 x plus 5/3 over x squared plus 2. Okay, so we're going to use the same trick that we have done earlier, times 3 times 3
times 3 times 3. Alright, so we have negative 1/3 times 3, that gives me negative 1. And then 1/3 x times 3, that will give me x. 5/3 times 3 will give me 5. Alright, that will be our partial fractions. Right, so we completed the whole videos on revisiting partial fractions when what you're given is a proper algebraic fractions. Okay, so the next video we'll be doing is what happens if you have an improper algebraic fractions. So how do we actually express that into partial fractions? So we'll learn that in the next video.